Here we're going to use the divergence theorem to calculate the flux of f across S. F of x, y, z in this case is going to equal the quantity of x cubed plus y cubed I plus the quantity of y cubed plus z cubed j plus the quantity of z cubed plus x cubed k. S is the sphere of radius 2 with center at the origin. Using the divergence theorem means that we're going to start by finding the divergence of f. Divergence of f will be 3x squared, because that's the partial with respect to x of x cubed plus y cubed, plus the partial with respect to y of y cubed plus z cubed, so 3y squared, plus the partial with respect to z of z cubed plus x cubed, and so 3z squared. The triple integral over E then of the divergence of f dv is equal to, well, folks, E is bounded by a sphere of radius 2, so I'm going to go with spherical coordinates. We have the entire sphere, and so we're going to let phi go from 0 to pi, theta go from 0 to 2 pi. Our sphere is of radius 2, so rho is going to go from 0 to 2. And as you can verify, 3x squared plus 3y squared plus 3z squared is the same as 3 rho squared. Converting to spherical coordinates means that we have our rho squared sine phi d rho d theta d phi. We can split this up into 3 different integrals. So we have 3 times the integral from 0 to pi of the sine of phi d phi times the integral from 0 to 2 pi of d theta times the integral from 0 to 2 of, it looks like we have 4 factors of rho, so rho to the 4th d rho. And I had to be a little bit careful here. My phis started to look like d's. It looked like dd. So let's make sure we're careful when we're writing our symbols. Well, this will integrate to 3 times negative cosine of phi, phi going from 0 to pi, times theta, well, theta goes from 0 to 2 pi, and it's just theta, so I'm just going to write 2 pi there, times 1/5 rho to the 5th, evaluated from 0 to 2. Quickly computing, we have this is going to be 6 times 2 times 32 pi all over 5. That'll give us a result of 384 pi over 5.